Well, good evening, everyone. Tonight we will be discussing the decisions that I have made based upon the risk information gathered throughout the class. So, I hope this is entertaining and informative. Basically, I identified three major areas where the lathe subsystem of the makerspace system can fail. Shrapnel exiting the area, electrical shock, and humans coming into contact with the actual part or tool or anything that can lacerate them, aka cut them. Um, so what I decided on the shrapnel was I broke it down into three basic causes. This would be human error, cutter overheating, or a lathe chuck slip. So they're pretty self-explanatory, but the only one that maybe is not is the lathe chuck slip. Basically, the lathe can not be gripping the material properly, which would be not enough force. Maybe it's the part is cockeyed in the jaws, things like that. But for the solutions that I analyzed, these were primarily found using dedicated function failure arrestor functions. For the human error, basically all you need to do is keep them trained and up to date in all the latest machining practices, make sure they're not getting lazy, perhaps switch them around to different machines to keep them engaged, make sure it's not just making the job monotonous, because we all know that we start daydreaming whenever our jobs become monotonous and bad things tend to happen. For the cutter overheating, one novel way of doing it is there are a few companies that produce lathe cutters that actually have slots for coolant to be passed through the tool themselves, so you don't have to take careful practice and time to aim the coolant tip, but you can actually just connect the coolant line straight to the tool and it'll cool both the part and the tool exactly what you needed. So this would alleviate a lot of the cutter overheating problems. Also, another way that many cutters overheat is them becoming dull after use. So if there was a way to keep an inventory of these cutters, and how many times they've been used, when was the last time they were sharpened, things like that, the likelihood of a operator using a dull cutting tool would be significantly reduced. For the lathe chuck slip, there are a few different ways that you could prevent this from happening. You could put pressure transducers in the jaws to make sure you're gripping properly, maybe vibration sensors on the axes so that you can see any vibrations that would be caused by the eccentric mass in the jaw. Also, with the pressure sensors in the jaws, you could measure the pressures against each other and see if one's gripping more than the others. This would throw up a red flag saying that, hey, something's bad here, you should fix it before you try to machine anything. The decisions that I made on this were that for the shrapnel leaving the workspace, it would be very easy to just encase it in a protective covering of some kind. Like many CNC lathes have protective doors that go over them. It wouldn't be too terribly difficult to make a door that still left the cranks for the system accessible and usable. For the tool cutting failure, both vibration sensing and the advanced coolant system um, would be put into place to prevent the cutter from overheating and thus breaking and bad things happening. Yep, that's pretty much it for that one. For the electrical shock, I broke it into two major categories: frayed wires and the fluid penetrating electrical subsystems. This would be, for example, if the fluid penetrates a sensor and shorts it out, it could damage the sensor itself, but also this short could be passed through the fluid into the frame of the lathe and come into contact with the human operator. So a couple of solutions for these would be for the frayed wires. Most of the time, the wires become frayed due to vibration, them sliding past a stationary object, or excessive bending, that kind of thing. To alleviate this, you could basically use a modified P-clip, which keeps the cable off of the frame. And with that P-clip, you can feed the wire through it. It would provide some dampening to any vibrations and would provide a much better solution to the frayed wires. For the fluid penetrating the electrical systems, this one's pretty easy. Basically, you just have to put gaskets around all the seals, all of the wire inputs and outputs to the systems, any hardware that you're mounting the system to the frame. That should be electrically isolated to make sure that there's no way that the electrical potential within the device can get to the frame of the lathe and out to the operator, because electrocution's not fun. So the decisions I made to prevent these from happening is to implement the specialized P-clips for the fraying wires, the gaskets within the electrical systems to prevent the fluids from penetrating them and causing a short. And also, even though the other two should be able to prevent any electrical incidents, it would be very cheap and easy to put a rubberized grip on anywhere where the operator would commonly come into contact with, such as the handles of the lathe, maybe the tool rack where you set your tools when you're not using them, the DRO panel, things like that. Alright, and finally, for the lacerations to the operator system. So this is a fun one. Basically, the part or the tool causes an injury to the operator that cuts them. I myself have had this happen many times with the lathes. Usually it's nothing bad, a little scrape here and there, but sometimes it can get very bad very quickly. So some of the causes of this would be I split this into purposeful interaction and accidental interaction. There are many times when operating a lathe where you have to come into contact with the part being machined. For example, like knocking off edges, you have to place a file on the spinning part and create a fillet. If you want to put any type of surface finish on it with an emery cloth, sandpaper, Scotch-Brite, things like that, you need to physically touch the part while it's spinning. And for the accidental interactions, that would be if the operator is just careless and his sleeve gets caught into the lathe, or if the tool or the part comes out and interacts with him in a very painful manner. Those would be the two major areas. Some solutions that I came up with for each is that for the purposeful interaction, the operator must have a very high level of experience with this and be watched by professionals the first couple dozen times that they do it to make sure that they're safe while they're doing it. It's necessary evil. Many times you need to have it done that way. For the accidental interactions, as with the solution, or for the first part, you can put a shield around the lathe itself, and basically the lathe would not turn on unless the shield was fully closed, forcing the operator to not come into contact with the part or the tool by accident and preventing it from contacting him in the event of an explosive cutter failure or the tool breaking off and launching at him. So yeah, those are my decisions for what I would implement into a lathe subsystem to make sure it's safer and more reliable than the current design. Thanks for watching.